Hi everyone, welcome back. In this lesson, we'll cover residual analysis and diagnosis checking, which involves the process of evaluating a statistical model by analyzing its assumptions and overall performance. Let's begin with residual analysis. Ideally, residuals should look like pure random noise. The goal of residual analysis is to check whether any patterns remain. If they do, the model specification likely needs improvement. There are 5 specific types of problems to look for when examining residuals. The first thing to check is lack of independence. The errors may be correlated with one another, violating a core assumption of least squares regression. Next is heteroscedasticity. The variability of observations may differ across levels of the predictor, breaking the constant variance assumption. We also want to watch for relationships with explanatory variables. If a predictor can explain part of the residual variation, it should be included in the model to improve predictions. Another concern is non-normal distributions. If residuals deviate significantly from normality, standard T and F inference procedures may not be valid. QQ plots help detect this. And finally, unusual points. Outliers or highly influential observations can disproportionately pull the fitted line away from the bulk of the data. Residual analysis is mainly conducted by analyzing standardized residuals, which are residuals that have been rescaled to be a dimensionless measure, typically a residual divided by a standard error. Using E sub I equals Y sub I minus Y hat sub I as the ith residual, the standardized residual can be defined in 3 ways. Each of these formulas, A, B, and C, define standardized residuals. They are not mathematically equivalent. Here, S is the residual standard deviation. H sub II is the ith leverage, which is defined as a measure of how much influence the ith observation has on its own fitted value Y hat I. We'll cover this topic in more detail in another video. And S sub I is the residual standard deviation after deleting the ith observation. An advantage of the first definition, A, is that it is easy to understand. The sample standard deviation of the residual is approximately S, so in this definition, we simply standardize E sub I by dividing by S. Definition B is a more precise definition that adjusts for leverage. The variance of the ith residual is sigma squared times 1 minus the ith leverage. Replacing sigma with the estimate S yields the standard error of E sub I. The standardized residual is E sub I divided by its standard error. Definition C is also known as the studentized residual. It is a modification of definition B and provides a better measure of unusual responses by excluding the ith observation from the calculation of S sub I. This approach prevents a large residual from inflating both the numerator and denominator, making it easier to detect outliers. Studentized residuals have another advantage. They follow a t-distribution with n minus p plus 1 degrees of freedom, assuming the errors are normally distributed. This property aids in the assessment of model fit, especially in small samples, and justifies the name studentized residuals, due to the relationship with the student's t-distribution. Residual analysis is crucial for identifying outliers, observations that are not well fit by the model. For example, an observation may be flagged as an outlier if its standardized residual exceeds 2 in absolute value. Under the standard normal distribution, about 5% of observations can be expected to surpass this threshold. Once an outlier is identified, there are 3 strategies for handling it. The first strategy is to include the outlier and comment on it. If there is no identifiable special cause, the observation may simply represent natural variability and might not meaningfully distort the overall results. Strategy 2 is to delete the observation. If the outlier is clearly unrepresentative of the population, removing it and reporting it separately is appropriate. Lastly, create a binary variable. If a known cause explains the outlier, a 0-1 indicator variable can be added to the model, formally accounting for the effect and automatically handling similar future observations. Residual analysis also plays a crucial role in improving model formulation by identifying additional explanatory variables that should be included. If the model is correctly specified, the residuals should look like pure random noise, with no systematic relationship to any variable. But if a predictor correlates with the residuals, it means that variable is explaining some of the remaining variation, and it belongs in the model. After fitting an initial model, we can follow these 3 steps to check whether additional variables are needed. The first step is to compute summary statistics for the standardized residuals. This gives an overview of the distribution and flags potential outliers. Next, we calculate the correlation between the residuals and any additional explanatory variables being considered. A non-zero correlation suggests a linear relationship worth including. Lastly, we can create scatter plots of the residuals against those candidate variables. This can reveal curved or nonlinear patterns that the correlation coefficient alone cannot capture. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.